Hey there, welcome back to Calculus. In this video, we're going to take a look at something called L'Hopital's rule. We've been analyzing the graphs of functions, and in particular, thinking about vertical and horizontal asymptotes. And in terms of calculus, those things are analyzed by taking limits, left and right-hand limits at vertical asymptotes, limits at infinity for horizontal. And L'Hopital's rule, the subject of this section, is a very useful device for taking limits. In the interesting case, we haven't used this a term before, but we have talked about it, the interesting case of a so-called indeterminate form, that is a limit of a fraction where both the numerator and the denominator are approaching zero or infinity. All right, so I'll kind of say why I'm calling those indeterminate forms, and then I want to show you how to use this result, L'Hopital's rule, as a way of calculating limits of those forms. And then there's actually a whole bunch of other indeterminate forms. We'll talk about why they come about, but it looks like I've got 5 others listed here, and I want to show you that each one of those 5 others, you basically have to do some algebra to convert it into one of the 2 above, and then you use L'Hopital's rule again. All right, so that's going to be the structure of the lecture. I'm going to try to do a lot of examples. I hope this video doesn't get too long, but you can always pause it. Another thing I'm going to say is I didn't include a lot of graphs here, so we're not going to look at a lot of these limit calculations graphically, but I hope you'll have a Desmos window open and just plot these functions as we go, so you can kind of visually confirm that the algebraic limits that we're calculating are correct. Okay, so I'm going to leave that to you. So let's get going. So first of all, why do we call these things indeterminate forms? So what are they? You're looking at limits of a fraction. So limits of the form where x is approaching something. That something can even be infinity. These can be limits at infinity. But the numerator and the denominator of the fraction are either both approaching zero or they're both approaching infinity. Yeah, so in the case that they're both approaching zero, then we call that a 0 over 0 form. If they're both approaching infinity, we call it an infinity over infinity form. So it's kind of a natural name. Why are they indeterminate? Well, because those limits may or may not exist, right? We've seen enough examples that depending on f and g, a limit of a fraction like that might exist and it might not. Let's just talk about this first one, the 0 over 0 case. We've talked about this before. When the numerator of a fraction is approaching 0, that's influencing the fraction to want to be small, to be close to 0. When the denominator of a fraction is approaching 0, it's making the ratio want to get big. So these things are kind of like exactly opposing each other. Yeah, so the 0 over 0 case is an interesting limit because of that opposition, and that limit might exist and it might not, and if it does exist, it could take on lots of different values. It depends on f and g. Same for infinity over infinity. It's just there the battle's kind of the other way. A numerator getting big makes the fraction want to get big. Denominators getting big makes the fraction want to get small. So that's the kind of the opposition there is who's going to dominate, numerator or denominator. So again, the word indeterminate is used just because, the outcome depends. There's no one definite answer, right? It can't be determined in one and only one way, so it's called indeterminate. Okay, we have some techniques to handle such things. Yeah, like this limit, what form is it? Maybe you could pause the video. When I'm asking that, I'm asking what are the numerator and denominator doing separately? So this first one, this rational function, I hope you checked, it's 0 over 0. Both the numerator and denominator of that function are approaching 0 as x approaches 1, and we had a technique to handle that. We factored. Yeah, so you factor that numerator into x minus 1 times x plus 1. And then we have a theorem that says that that limit is going to be the same as the limit as x approaches 1 of x plus 1, which is 2. So in that indeterminate form, the limit exists and the ratio equals 2. Or we also know how to handle this. This is a limit at infinity. It's a quadratic polynomial over a quadratic polynomial. We have a technique for that. You divide everything by the highest power of x. If I divide everything by x squared here and simplify as I go, the numerator would look like that. The denominator would be 3 plus 1 over x plus 5 over x squared. And then these terms, the terms with x's in the denominator but not the numerator, they're all approaching 0. Yeah, because big denominators make the fraction want to get small. So in that case, we see that the limit is a third. Yeah, so we have techniques to handle. This is, I should have said it, this is an infinity over infinity limit. Both the numerator and denominator of that expression are getting big as x goes to infinity. So we have some methods, but what about things like this? What about the limit as x goes to 1 of log x over x minus 1? That's a 0 over 0 limit. The logarithm as x approaches 1 is approaching 0. And as x approaches 1, so does x minus 1. But we can't factor it. It's not a polynomial. It doesn't have a highest degree. So the methods above don't apply. Same thing here. This one's infinity over infinity. The logarithm as x goes to infinity grows without bound, and so will x minus 1. Yeah, so how do we handle those? That's what L'Hopital is built to do. Okay, so let me show you the rule. I'm not going to prove it. I'm not going to give a proof of L'Hopital's rule. I'm just going to state it here without proof. Here is its statement. So you have these two functions. They have to be differentiable, yeah, and the derivative of the denominator can't be 0 around some point. And the limits are either both 0 or both infinity. And with infinity, I don't even care if one of them is plus infinity, the other one's minus. In all four cases, I'll just call them infinity over infinity forms. Okay, so 0 over 0 or infinity over infinity. And what L'Hopital's rule says is that if you want to compute that limit, you want to compute the limit as x approaches a, and a could even be infinity of that ratio, you can compute it by computing the limit of the ratio of the derivatives. All right, so you just take the limit of f prime over g prime. I want to emphasize here, no quotient rule. Right? L'Hopital's rule is not saying take the derivative of f over g. It's saying that the limit of f over g is the limit of f prime over g prime if the other one exists. Yeah, so if the other side exists or is minus infinity or plus infinity. All right, just as a comment here, L'Hopital's rule works for one-sided limits. It works for limits at infinity. So the author here has written it just once, but it's actually quite general. It works for every kind of limit that we know. Let's try it out. First example I want to do is that log x over x minus 1. That's a 0 over 0 limit. The numerator and denominator are both approaching 0. So L'Hopital's rule, I usually like to write his initials over the equal sign, says that that limit is the same as the limit as x approaches 1 of the derivative of log x, that's 1 over the derivative of x minus 1, that's 1. And that's a substitutable limit. That's 1 over 1. So the original limit is equal to 1 by L'Hopital's rule. Cool. Check it with a graph. I hope that you'll stop this right now, go to Desmos and graph y equals log x over x minus 1 and look at the graph near x equals 1, and you're going to see that the y coordinate is close to 1. Nice. Let's just do some of these things kind of rapid fire style here. This one is infinity over infinity. Both the numerator and denominator are approaching infinity. So that's what you have to check before you apply the rule. And L'Hopital's rule says that this limit as x goes to infinity would be the same as the limit of the ratio of the derivatives. All right, well, that's just the limit as x goes to infinity of 1 over x. 1 over x divided by 1 is 1 over x, and that's going to be 0. So again, you've already graphed this function, I hope, if you took my advice. Look out to the right. It should have a y, a horizontal asymptote, y equals 0. Yeah, horizontal asymptote equation, y equals 0 is what that limit calculation tells us. Nice. Let's just practice. Here, the old technique would have worked. Pause the video and answer this yourself. What kind of form is this? What kind of form is it? It's infinity over infinity. Yeah. So our old technique would work. You can see the answer is a third. I hope you can see the answer is a third. What would L'Hopital's rule say? So L'Hopital's rule says that this limit is the same thing as the limit as x goes to infinity of the limit of the derivatives. These are polynomials, so we can make quick work out of differentiating them. Yeah, this thing's still infinity over infinity. So we can apply L'Hopital's rule again. It's the purpose of this example, actually. Sometimes before you get a limit that you can actually successfully evaluate, you have to apply the limit, the L'Hopital's rule maybe more than once. Here we have a constant, 2 over 6, and that limit is equal to a third. All right, check it with a graph. Horizontal asymptote, y equals a third is the equation. That's what we just found for that rational function. So you don't have to use that old technique from chapter 2 if you don't want to, although I think the technique from chapter 2 is more efficient for such a rational function, but L'Hopital will work as long as it's one of the two forms. It's important to check this. And the limit that came out had the same form, so we could use L'Hopital's rule again. Cool. All right, we're doing good here. How about this one? What form is this? As x goes to infinity, what happens to x cubed and e to the x separately? Dramatic pause. It's infinity over infinity limit. So what does L'Hopital's rule say? You don't have to write this LH there if you don't want to. It's the limit as x goes to infinity of the derivative, 3x squared. Derivative of e to the x is e to the x. That's still infinity over infinity. So I'm going to L'Hopital it again. I don't know if I'm allowed to use L'Hopital as a verb, but I just did. It's still infinity over infinity. Well, so we'll just keep doing this here. Take L'Hopital's rule again. Never am I using the quotient rule, notice. Yeah, I'm just differentiating the numerator and denominator separately. And now that's not an infinity over infinity form. It's not an infinity over infinity form. I didn't line these things up very well, but this one, the denominator is going to infinity, but the numerator is not, so that limit is 0. Yeah, so the original limit is 0. And by the way, I won't make the video longer by writing it, but we had to use L'Hopital's rule, what, once, twice, 3 times, because that's how long it took to differentiate that polynomial before we got a constant. Yeah. So if this polynomial had been degree 4, then I would have had to differentiate. I would have to use L'Hopital's rule 4 times, but we still would have got 0. If the polynomial had been degree 8, we would have to use L'Hopital's rule 8 times, but we'd still get 0. So if you take any polynomial over e to the x, the limit as x goes to infinity of that ratio is going to be 0 for the same reason. Yeah, exponential functions grow faster. In this case, all I've shown is x cubed, so I'm going to show that. But you could put any power of x up there. Yeah. Why do I say e to the x grows faster than it? Because when I look at their ratio as x goes to infinity, the ratio was 0. That means the denominator of this fraction is much, much bigger than the numerator when x is large. So that's my interpretation of that. And in fact, e to the x grows faster than any polynomial. Any polynomial. Cool. Here's kind of a cautionary example. You can see my warning sign over here. If I just applied L'Hopital's rule without checking, I would write something like, this is the limit as x goes to pi from the left, pardon me. The derivative of sine is cosine. The derivative of 1 minus cosine is sine. So that's the cotangent function. So the cotangent is approaching -1. The sine is approaching 0. So this limit doesn't exist. That limit doesn't exist. Yeah, the numerator is approaching -1, whereas the denominator is approaching 0. The denominator, as we approach pi from the left, would be positive. So if you like, I could write that this is minus infinity, but it doesn't exist. But this calculation is wrong. If you take a look at the graph of this thing, you're going to see that near x equals pi, that limit is not negative infinity. So where did we go wrong? I applied L'Hopital's rule in a situation where I couldn't, because sine x over x, this limit, it's not 0 over 0 or infinity over infinity. Yeah, because as x goes to pi from the left, the sine of x is approaching 0. Yeah, the 1 minus the cosine of x, excuse me, is approaching 1 minus -1. That's 2. Yeah, so this limit, the limit as x approaches pi from the left, it's not like we can't do it, of sine x over 1 minus cosine x, it's 0 over 2, or 0. All right, so what's my cautionary tale? Don't use L'Hopital's rule if you haven't checked the hypotheses. If it's not a 0 over 0 limit or infinity over infinity limit, it'll give you garbage answers in general. Okay, you might luck out every now and then and get a correct answer, but you don't want to take the chance. All right, Okay, we're doing good. Those are all the examples of the straightforward L'Hopital's rule, 0 over 0. I want to tell you about those other indeterminate forms. Okay, so I think the best way to do this is just to kind of look at something from your text. So another kind of indeterminate form is this 0 times infinity. So why is it indeterminate? Here, the battle is sort of different. When you're multiplying two numbers, if one of them is trying to become like 0, that's influencing the product to be small. Yeah. So this one factor approaching 0 wants the product to be 0. If one of the factors is approaching infinity, that makes the product want to be big. So that's the kind of opposition. Yeah. So how we deal with that is we rewrite those products algebraically as fractions. Yeah. So, for example, if f is going to 0 and g is going to infinity, then this thing is going to be a 0 over 0 form. If f is going to infinity and g is going to 0, then this is going to be this will be a 0 over 0 form as well. All right. So you can rewrite those things into one of those two forms. Let's look at this example just to illustrate it. So I've got x times log x. So maybe you need to do this slower than what I'm talking about. Get out some graphs. But as x goes to 0 from the right, certainly x is approaching 0. And maybe you remember that the logarithm as x approaches 0 from the right is going to negative infinity. So again, I don't worry about the negative part. I'm calling this a 0 times infinity form. So how I'm going to handle this is I'm going to rewrite this limit. I'm going to say it's the limit as x goes to 0. And then I'm going to write it as, instead of x times log x, I'm going to write it as log x divided by the reciprocal of 1 over of x. Yeah. So algebraically, multiplying by x and dividing by 1 over x are the same thing. And now this guy is an infinity over infinity form as x goes to 0 from the right. Yeah. So now we can take the derivative using L'Hopital's rule. Calculate the limit rather using L'Hopital's rule. So it's the limit as x goes to 0 from the right. Derivative of the natural log is 1 over x. The derivative of 1 over x is minus 1 over x squared. Yeah. Okay, how does that simplify a little bit? Well, it's a fraction of a fraction. So you can check the math. You can do lots of things. You can multiply it by the reciprocal of the denominator or whatever you like to do, but that fraction reduces to just minus x. Minus 1 over x divided by minus 1 over x squared is just minus x, and that limit we can see is 0. Okay, so summary, if you're given a product, you rewrite it as a fraction. I had a choice. I ended up writing this fraction as log x over 1 over x. I could have written x over 1 over log x. The differentiation would have been more complicated. So you never know which one. You try one, and if it feels like it's getting unreasonably difficult, try to rewrite it in a fraction in the other way. Okay? Good. So what other kind of indeterminate forms do we have? Well, you can look at indeterminate differences. Indeterminate differences. What do you mean by that? You're looking at an expression f minus g, and both f and g are growing without bound. So that could be an answer anywhere from infinity to minus infinity to some number. Yeah, is it like the author is saying here? Is the answer infinity? F is getting bigger faster. Is it negative infinity? G is getting bigger faster. Maybe their difference is some finite number. Here's an example. I've got 1 as x goes to 1 from the right. The logarithm approaches 0, so 1 over it is approaching infinity. And I'm subtracting something that's also approaching infinity. So that's an infinity over infinity form. And the technique to handle such things is, well, basically get a common denominator and turn it into a fraction. Every one of these things, the technique is to put it back into one of the two original forms. So here, let's just do it. I'm going to just get a common denominator. So I'll write this fraction difference as x minus 1 minus log x over the product. All right, let's check what happens to that. If we look at the numerator first, as x approaches 1 from the right, well, that term is going to go to 0. So is the logarithm. So the numerator is approaching 0. How about the denominator? Well, x is approaching 1, so that's going to 0. The log is approaching 0. 0 times 0 is 0. So we've converted this into a 0 over 0 form. Okay, this is a 0 over 0 form. I can't line those up very well today. So L'Hopital's rule applies. Differentiation is going to be a little bit more complicated this time. In the denominator, we have to use the product rule. In the numerator, it's not bad. It's 1 take away 0 minus 1 over x. Okay, that's the derivative of our numerator. The denominator, we got to use the product rule. So it's the derivative of x minus 1, that's 1 times log x, minus x minus 1 times the derivative of log x. It's 1 over x. And that, I would have to simplify a little bit before I can see what's going on. The numerator is 1 minus 1 over x. The denominator is log x. What do we got? 1 over x times x is 1, so that's minus 1 plus 1 over x. And now we let x approach 1 from the right. The numerator is going to approach 0. The denominator is going to approach, well, 0, take away 1 plus 1. That's also 0. So we have to use L'Hopital's rule again. All right, so differentiating again, top and bottom. The derivative of the top this time is minus 1 over x squared. Excuse me, minus 1 over x squared. It's plus 1 over x squared. Derivative of log is 1 over x. The derivative of 1 over x is minus 1 over x squared. And now, letting x approach 1, the numerator of this fraction is approaching the number 1. The denominator is approaching the number 0. And the numerator is approaching 1 from the positive side. 1 over x squared from the right is less. So this limit doesn't exist. The numerator is going to a non-zero number. The denominator is going to 0. So it's positive infinity. That limit is positive infinity. Cool. All right, last kind of thing. I know this has been a lot of stuff to swallow here, but you just kind of have to practice this business. But there are lots of indeterminate forms that come from raising one function to another. In all cases, it's sort of the same kind of battle. So you have one function, f of x, and it's raised to g of x, and you're taking the limit. Here, the author does not, that's a typo, there should be no equal sign right there. So it's the limit of that expression. That's what we're wondering. And if both those things go to 0, a base going to 0 makes something want to be 0. Its exponent going to 0 makes it want to be 1. So that's this indeterminate form 0 to the 0. The base goes to infinity and the exponent goes to 0, oppose each other. The base going to 1 and the exponent going to infinity oppose each other. We're going to treat all such cases by taking logarithms. You take logarithms because when you take a logarithm, an exponent can be written as a coefficient. So you'll basically turn one of these into an intermediate product, which you'll then rewrite as a fraction and handle with L'Hopital's rule. All right, so this is kind of the most sophisticated example. Let's see if we can try it. Here I've got a 0 to the 0 limit. I'm taking the limit as x goes to 0 from the right of the very intimidating looking function x to the x. And I want to know, how does x to the x behave? The base going to 0 makes it want to be 0. The exponent going to 0 makes it want to be 1. So we'll see what happens. So the idea is that we start off by sort of naming this function something like y. And then we take the log of y. Using logarithm properties, the log of y, you can bring down that exponent. It's going to be x times the log of x, right? By the logarithm properties. And then we'll take the limit as x goes to 0 from the right of the log of y. If I rewrite this, maybe you recognize it. X times log of x is just our friend. So we're just taking the limit as x goes to 0 from the right of the log of x over 1 over x. We actually computed this limit above, but I can't remember what the answer was, so I'm going to compute it again by L'Hopital's rule. That's a 0, an infinity over infinity limit. So by L'Hopital's rule, that's the limit as x goes to 0 from the right of 1 over x over minus 1 over x squared. which just like above, I'm starting to remember now, that was minus x, that's 0. But we have to be a little bit careful. So what we just computed is that as x goes to 0 from the right, the logarithm of this variable y goes to 0. So if you want to know what y does by continuity, y, which is e to the natural logarithm of y, is going to go to e to the 0. It's by the continuity of the exponential function, which is 1. So to summarize, the limit as x goes to 0 from the right of x to the x is equal to 1. Okay. Well, I hope you were pausing a lot, and I hope you were drawing lots of graphs as I went. I know I was talking fast, but I didn't want to make this video too long. But that is a very useful computational tool for limits of certain forms called L'Hopital's rule. And thanks for listening.